Good morning, students. I welcome you all to the next session on the topic of mechanical vibrations. Today is the 31st of January. It's almost 8:30. And what I see is that all of you have already joined this particular class. And if my voice is visible, is audible, kindly let me know. Or let me just write a message in the WhatsApp group. Just a moment.
Yes, sir.
Okay, then. Since I'm audible, so let me just start with this particular session. And as you might have noticed that we have shifted from Google Meet to Zoom. This is primarily because the college faculty is for the time being not able to record the lectures on Google Meet because of some unknown problems. And since all of you put a demand to share the lectures which have been delivered, so therefore the recording becomes a necessity. And obviously the sharing is being done through the YouTube channel. There are 3 lectures, or let's say 3 playlists which have been posted in my channel. One corresponds to finite element, that obviously is for the MTech thermal students. That is regarding the course which you have already studied in your previous semester. Now, apart from this particular playlist of FEM, there are 2 more lists which have been created. One of them happens to be the mechanical vibration itself, which of course is according to the book by Groover. I am practically following the same sequence of chapters which have been illustrated in Groover. And there is another list also that is by nonlinear dynamics. So that corresponds to your curriculum. And I suppose, just a moment. I suppose all of you are going through that particular list also. Can somebody actually confirm me that the tool playlist, that is the playlist of vibrations, and the other playlist of nonlinear dynamics, these two lists are actually available in my channel? सबको दिखाई तो दे रहा है ना?
Yes, sir.
Okay then. And last week on Monday, there was a lecture posted on the topic of damped free vibrations. Let me just clarify as far as the terminology is concerned. Damped free vibration means that there is some amount of damping present and there is no external excitation. So this becomes damped free vibration. Undamped free vibration means undamped free vibrations means that there is no damping present and there is no external source also. And damped forced vibration means that there is damping present and there is some forced vibration also. So this is as far as how the terminology goes. And if this particular lecture on undamped free vibration is clear, we can move forward with one of the solved examples. Otherwise, if there is any problem regarding relating to this thing, kindly let me know so that I can try to resolve it. किसी ने कुछ पूछना है regarding this thing? Okay, then in that case, let me just bring one of the examples on display. Just a moment. Okay, now, I suppose the example is on display now. Let me read out the sentence, the problem that is. A gun barrel of mass 600 kg has a recoil spring of stiffness 294,000 Newton per meter. That means that the mass of the gun is given and the recoil spring is the stiffness of the recoil spring. This is also a known quantity. This thing is visible to all of you now. Can somebody actually confirm this thing?
Yes, sir.
Okay.
Yes, sir.
Okay, thank you. So this particular problem consists of a gun. Obviously, the construction of the gun is something which all of you are already aware of. There is a hollow cylinder, basically, which is known as the gun barrel. And this is used to launch some rockets or projectile sort of things. So the mass of the barrel happens to be 600 kg. And to the barrel, there is attached a stiffness given by 294,000 Newton per meter. Now, once the projectile has been launched, the barrel, that is the hollow cylinder, recoils through a distance of 1.3 meter. Okay, this is the backward stroke. Okay, I have a figure, obviously something over here. So this particular thing happens to be the hollow cylinder. This is the projectile P, and to the barrel B, there is a spring K which has been attached. Obviously, the value of the mass and the stiffness is given. So the first part of the problem is that the barrel recoils by a distance of 1.3 meter on firing. Okay. So obviously this means, just a moment. The first problem is to find the initial recoil velocity of the barrel. So let me come to the figure once again. This particular barrel has been attached to a spring, and the barrel recoils through a distance of 1.3 meter. That is this thing over here. So obviously, if the mass of the if the mass is known, obviously we can conserve the energy to find out the initial velocity of the barrel. Okay, we know the stiffness of the spring, we know the distance through which the mass recoils, we know the mass of the gun barrel itself. So simply the conservation of the two energies, that is the kinetic energy of the barrel and the strain energy of the spring. These two can be balanced together to find out the velocity of the gun barrel, initial velocity. So that is going to come out to be something like 28.75 meter per second. Obviously, this is elementary applied mechanics. So I suppose this is going to be clear. Nothing, no sort of doubt might be existing in this particular problem. So let me just come to the second part of the query. Now the construction is that there happens to be a dashpot which is going to act as a damper. There happens to be a dashpot attached to the barrel, and the thing is, two additional informations regarding this dashpot is also given. The first information is that of course, this particular dashpot is going to have some amount of damping. So the damping which is present in the dashpot happens to be the critical damping. Okay, the system is not over damped, it is not under damped, but it is critically damped. Okay, this is one of the informations which have been given. And the other thing is that there is a particular instant at which the damper is going to be activated. And it is going to be activated, or it is going to be engaged at the end of the recoil stroke. Recoil stroke is something which can be explained with respect to the figure. So once the projectile moves out, the barrel obviously is going to move in the backward direction. So this particular motion of the barrel in the backward direction is known as the recoil stroke. And the recoil length is something about 1.3 meters. So this is one thing which is already given in the problem. The recoil stroke is 1.3 meter. So the damper is going to be activated not during this recoil stroke. Okay. It is going to be activated when the barrel is moving in the towards the inward stroke. It is coming back. It is not moving towards the front or towards the left, but the damper is going to be activated when the barrel is moving in the right direction. So this obviously means that when the mass is moving towards the left, okay, when the mass is moving towards the left, the nature of vibration happens to be free. There is no damping present, that is undamped, and there is no external excitation present. So it is free. So during the starting of the backward stroke, recoil stroke, the motion happens to be undamped, free vibration. This is the reason because we have been able to balance the two forms of energies which are present during this particular part of the motion. But when the recoil is over, the barrel is going to come towards the inward position. And during this particular instant, the damper is going to be activated. So this means that the inward stroke is going to be damped because there is a damping present, and it is going to be free also because there is no external excitation. So during this part of the inward stroke, the formula which is going to govern the motion is going to be given by the second order equation, which I am writing just now. Mx double dot plus Cx dot plus Kx is equal to 0. This is the equation which is applicable for the return part of the recoil stroke. And the other part, that is when I neglect the damping, the equation becomes mx double dot plus kx is equal to 0. This equation is valid during the outward motion of the recoil stroke. Now, since it is already given that the damping which is present happens to be critically damped, I can use some of the formulas which were derived in the theoretical lecture to find the actual amount of damping present in the system. For this, let me just bring another slide on display. Now, since the damping happens to be critically damped, this is one of the formulas which relates the properties of the system to the critical damping. This is one particular equation which we have already derived in the theoretical classes. And when you substitute the value of stiffness K and mass M into this formula, the actual amount of critical damping comes out to be something like 26600. That is 2,66,600, 26,600 Newton second per meter. The 26,600 Newton second per meter is the amount of damping, which of course is the critical damping. And using all the informations which have been given to us, I can also find the natural frequency of the system, because this is not the damped frequency of vibrations. This is the natural frequency of the system given by under root of K over M, which comes out to be 22.1 radians per second. Now coming to the last part of the problem. Just a moment. Just a moment. The last part of the problem is that we require to find the time taken for the barrel to return to a position, 5 centimeter from the initial position. To return to a position 5 centimeter from the initial position. So this means that the barrel is going to move in the backward direction, and then it will move towards the inward direction, and this much distance is supposed to be 5 centimeter. Okay. In the initial position, the spring was not deformed. Okay. In the initial position, the spring was not deformed. As the recoil stroke starts, the spring is going to be deformed. It is going to be deformed to the maximum extent of 1.3 meter when the recoil stroke is over. And then it is going to come back towards the initial position. That is, the inward stroke is going to start. And obviously, as the inward stroke is in motion, inward stroke is in motion, the length of the spring will go on increasing. Okay, the length of the spring will go on increasing, and at one point of time, it is going to be, the compression of the spring is going to be only 5 centimeter. So we are supposed to find the time needed for the barrel to return to a position 5 centimeter from the initial position. So for this, let me just okay. One more thing which I missed out is that when the spring was under the recoil stroke, the damper obviously is not present. But since we have found the natural frequency of vibration, the time period for this outward motion of the recoil stroke is going to be 1/4 of the time period. The time taken for the outward motion of the recoil is going to be 1/4 of the time period. Since I know the natural frequency omega n, I can obviously find this 1/4 time period, which comes out to be somewhere around 0.071 second. So this much of the time is required for the barrel to move outwards when the damper was not activated. Now for the inward motion, this is where the complexity starts. For the inward motion of the recoil stroke, the damper is active. It is actually in picture. And the value of the damping happens to be critically damped. And under this case, the equation of displacement is given by the expression over here. In fact, if you remember the theoretical developments, during this part of the motion, for this particular equation, the two roots come out to be equal. Okay? The two roots of vibration comes out to be equal. Therefore, there is a value T which has been placed at this position. And as far as the values of C1 and C2 are concerned, they are going to be found using the initial conditions which have been supplied to us. So let me just come back to the last part of this particular problem. Just a moment. There appear to be something wrong. Now, suppose this particular slide is given, is visible. This is actually the third slide of the solution. So I suppose this is visible. And it reads something as x dot is equal to C2 e raised to power minus omega n. Is this visible to all of you? Is this?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So this particular slide obviously corresponds to the velocity and has been found by using the displacement equation, which was on display in the previous slide, given by C1 plus C2 times T whole multiplied by e raised to power minus omega n into T. This is the displacement equation, which is applicable for critically damped oscillation. And obviously, once you take the differential of this equation with respect to time, what you get is the formula for the velocity given by this expression. Now, obviously, C1 and C2 are unknown quantities. They are going to be found using the initial velocities. So, with respect to the initial undeformed length of the spring, okay, the initial values have been provided with respect to the initial undeformed length of the spring. So the initial extension is x naught and the initial velocity happens to be 0. This I suppose are two things which are clear to all of you. And once these two expressions have been substituted in the equation, the value of C1 and C2 can obviously be found. And please notice one thing more, that at this particular location, this is the location where time t happens to be 0. Okay. So once the value of C1 and C2 have been found, this is C1, this is C2. This, of course, is omega n, because I have this thing over here. And the thing is that this particular equation actually is a non-linear equation. It is not a linear equation because there happens to be a exponential term over here. And on top of that, it has been multiplied by the presence of time in this term also. So this equation happens to be a nonlinear equation, and the value of x is supposed to be 0.05, which has been supplied in the problem. So the thing is that how this particular nonlinear equation is going to be solved. And this has to be solved in a hit and trial manner. For example, if you substitute the value of t to be, let's say, 1 second, just assuming that this much amount of time is going to be enough for the barrel to return to a position 0.05 meter from the equilibrium. So if this much time is going to be enough, you are going to get some value of time, some value of displacement x, which might be 0.05, or it might be less than, it might be actually more than that also. So this is going to give you an indication whether the time t is equal to 1. It has to be increased or it has to be decreased. So likewise, you are going to calculate this particular equation iteratively, that is the hit and trial manner. And obviously, after some hit and trials have been made, you are going to arrive at a correct solution, which happens to be 0.22 seconds in this particular case. And this 0.22 is the time period, is the time required for the barrel to return to the equilibrium position. Okay, it is not the total time for which the barrel was in motion. Okay, it is the time which is going to be taken by the barrel to return back to the equilibrium position. That is the return stroke. And this particular diagram is the history of the motion. So the barrel or the projectile is fired at this particular instant. And for the first half of the motion, which is in fact, the backward stroke, during which there was no damper present. So obviously, this is going to be the natural oscillation, for which the time is going to be 1/4 of the time period. This is from here to this much. Okay, so this means that the barrel is going in this direction. And once the backward stroke is over, it will then move in the inward direction. That means in the opposite direction. So during this opposite direction, from this point to this point, this is the forward stroke, for which damping is actually going to be present. And this is going to be critically damped. And this much time happens to be 0.22 seconds. So this much time, 0.22 added by t by 4 over here, gives you the entire time for which the barrel was in motion. Okay. And ultimately the barrel settles down to a position of 0.05 meter from the unstretched position of the spring. So this is one of the best examples which I was able to find in the book. Of course, it appears as a solved example in the book by Gruber, but compared to the rest of the examples which are present in at least in the book by Gruber, they happen to be pretty straightforward. Therefore, this was the example which was chosen to be discussed in the class. Now, if there is anything which is not clear regarding the method in which this equation has been solved, kindly let me know so that I can discuss it once again. Anything which is not clear? Okay, then the other thing is,
Sir,
there is at least one person who is speaking. बोलिए.
sir, can you explain how damping came into play only for the return stock or the?
No, the thing is just a moment. Let me bring the question on display once again. The thing is, it is, I suppose this problem, statement of the problem is clear, is visible to all of you. It is already specified in the problem that the dashpot is engaged at the end of the recoil. It is already given that the dashpot is going to be engaged at the end of the recoil. Okay. As I can explain you the working of this particular projectile once again. Let me just try to understand how that is going to be done. I cannot find. Actually, there is supposed to be a whiteboard over here in which I could have drawn some drawings. Let me just. Okay, then let me just at least bring okay, here it is. Okay, then. So a white screen has appeared in front of all of you. So as far as the construction of the that particular gun is concerned, there is simply a hollow cylinder in which the projectile is going to be placed, and obviously this projectile is going to move forward. And as this projectile is moving forward, the barrel obviously is going to move in the backward direction. So for that particular purpose, there is a spring which has been attached for constraining the backward motion of the this particular barrel. During the backward portion, there is only the spring which is going to come into picture. And then when the barrel has moved to the backmost position somewhere over here, this is the end of the recoil stroke. Okay, this is the end of the recoil stroke. At this particular instant, somehow the damper or the critically damped damper is going to be activated. And then from this particular position, the barrel is going to move in the inward direction. The first motion was outward motion of the recoil. Now it is going to be the inward of the recoil. And in the beginning of the inward motion, the damper C is going to come into analysis. How it is getting activated, or what is the actual mechanism which activates it, this is of course not our concern. The thing is that the damper is going to be in the analysis only during the inward motion of the recoil stroke. So I suppose this is clear now. Any other query or something more to be discussed over here? Anything else to be discussed?
Sir.
हाँ बताइए. हाँ गोपाली. हाँ
सर वो जो आपने x की वैल्यू निकाली है, x की इक्वेशन, वो एक बार और बता दीजिए, क्योंकि उसमें थोड़ा कंफ्यूजन है. एक बार स्लाइड आ जाती है.
लेकिन आप कौन से इक्वेशन की बात कर रहे हैं, ये तो बताइए आप मुझे.
सर जो x की वैल्यू मतलब वेलोसिटी और पोजीशन के लिए हमने निकाला था क्रिटिकली डैम्प्ड के लिए डैम्पिंग.
जस्ट अ मोमेंट. एक मिनट रुको जरा सा. इस इक्वेशन की बात कर रहे हैं, ये इक्वेशन.
नो सर,
इसके
जो
बाद
क्रिटिकली डैम्प्ड के लिए हमने हाँ
इसके
डिराइव
बाद
करी थी।
इसके बाद जो हुआ था
Yes, sir.
ये वाला, इसकी बात कर रहे हैं।
यस सर। सर इसमें जो हमने एक्स की वैल्यू पुट करी है, मतलब कंडीशन लगाने के लिए C1 C2 निकालने के बाद की।
हाँ तो
सर तो उसमें एक्स की वैल्यू जो एक्स ये है, एक्स वो कहाँ से हमने लिया, इनिशियल पोजीशन से या
हाँ
रिकॉइल स्ट्रोक के बाद से?
नहीं, स्प्रिंग की इनिशियल पोजीशन से। आपको यू माइट रिमेम्बर दैट all equations which have been derived are from the equilibrium position of the spring. They are from the equilibrium position of the spring. और ये जो प्रेजेंट केस है, इस केस में स्प्रिंग की इक्विलिब्रियम पोजीशन क्या होगी? When the spring is not deformed. ठीक है, वहां से लिया गया है। ठीक
तो
है,
सर जो टाइम आएगा वो एक बार कंप्रेस होने के बाद 5 सेंटीमीटर तक पहुंचने तक का पूरा टाइम आएगा ना?
नहीं, एक मिनट रुको। ये जो स्प्रिंग है, ये फिगर तो डिस्प्ले पे आ गया होगा, ठीक है।
यस
ये जो क्या कहना चाहिए, ये जो बैरल की पोजीशन है, इस बैरल की इस स्टार्टिंग पोजीशन पर स्प्रिंग जो है वो अनस्ट्रेच्ड है, ठीक है। ये स्प्रिंग की इनिशियल लेंथ है, ठीक है। तो जब आपका जब बैरल आपका आउटवर्ड स्ट्रोक करता है, ठीक है, जब बैरल यहां से पीछे तक जाता है, तो ये आपका अनडैम्प्ड वाइब्रेशंस हैं, अनडैम्प्ड फ्री वाइब्रेशन है, जिसमें जो इक्वेशन एप्लीकेबल होता है दैट इज गोइंग टू बी mx डबल डॉट प्लस kx इज इक्वल टू 0, ठीक है। दिस इज क्लियर?
यस सर।
ठीक है, दिस बेसिकली इज इस मोशन में जो, अगर आपको टाइम पीरियड निकालना है तो यू सिंपली फाइंड आउट द नेचुरल फ्रीक्वेंसी एंड मैनिपुलेट दिस नेचुरल फ्रीक्वेंसी टू फाइंड द टाइम पीरियड। यहाँ इस नेचुरल फ्रीक्वेंसी से टाइम पीरियड निकला है, दिस इज टाइम पीरियड फॉर वन ऑसिलेशन, ठीक है। लेकिन जो आपका डैम्पर है, ये जो आपका बैरल है, उसको यहां से पीछे तक जाने के लिए तो सिर्फ 1/4 ऑसिलेशन हुआ ना, ठीक है। ये यहां से पीछे गया, फिर यहां गया, फिर यहां गया, फिर यहां आया, तो ये तो सिर्फ 1/4 ही तो ऑसिलेशन हुआ, ठीक है।
यस सर।
तो इनिशियल पोजीशन से एंड स्ट्रोक तक जाने के लिए टाइम रिक्वायर्ड इज गोइंग टू बी टाइम पीरियड डिवाइडेड बाय 4, ठीक है। दिस इज फर्स्ट पार्ट ऑफ द स्टोरी, ठीक है। अब इसके बाद द बैरल इज सपोज्ड टू कम बैक, एंड for the barrel to come back, the equation of motion is going to be mx double dot plus cx dot plus kx is equal to 0, ठीक है। ये आपका डैम्प्ड ऑसिलेशंस का केस है अब ये, ठीक है, डैम्प्ड फ्री ऑसिलेशन का केस है, ठीक है। एंड बिकॉज इन दिस पर्टिकुलर केस दिस इज द रिटर्न स्ट्रोक, ठीक है। ये आउटवर्ड स्ट्रोक नहीं है, दिस इज द रिटर्न स्ट्रोक for which this is the governing equation, and since the damping is critically damped, okay, damping is not over damped, it is not under damped, it is critically damped, क्योंकि वो critically damped है, इसलिए जो equation of motion आएगा आपका वो ये चीज होगी, x is equal to c1 plus c2 into t, because for critically damped oscillations both the roots are equal, इसलिए ये टाइम की वैल्यू यहाँ पे एक्स्ट्रा आती है, एडिशनल आती है। दिस इज इक्वेशन फॉर डिस्प्लेसमेंट। इसको जब आप और अब इसमें टी क्या आता है, ठीक है, दैट इज द प्रॉब्लम। टी इज गोइंग टू बी मेजर्ड जहां से आप इनिशियल वेलोसिटी देते हैं, ठीक है, इनिशियल वैल्यू जहां से आ रही है, तो इसमें इनिशियल कंडीशन हम कहां से दे रहे हैं? फ्रॉम द स्टार्टिंग ऑफ द इनवर्ड स्ट्रोक, ठीक है। हम टी दे रहे हैं फ्रॉम द स्टार्टिंग ऑफ द इनवर्ड स्ट्रोक, यहां से टी दिया जा रहा है, ठीक है। एट दिस पर्टिकुलर पोजीशन टी नॉट इज 0, जो इनिशियल कंडीशन है वो यहां पर है, which is x naught is equal to something like 1.3 and x dot naught happens to be 0. तो टाइम t यहां से दिया जा रहा है और इसके बाद ऑब्वियसली दिस मीन्स कि जो डैम्पर का फिगर है वो कुछ इस तरह से आएगा मोशन. ठीक है, दिस इज टाइम t on the x-axis and this is displacement x on the y-axis, and at this particular point displacement happens to be 1.3, or at the end this condition is given, this is 0.05 और मुझे वो टाइम चाहिए. मेरे ख्याल से अब क्लियर होना चाहिए. Okay, then anything else? Because this particular problem happens to be typical ना, इस प्रॉब्लम में दो अलग अलग मोशंस को क्लब करा गया है. ठीक है, दो अलग अलग मोशंस को क्लब करा गया है. वन पार्ट ऑफ द मोशन इज फ्री ऑसिलेशन जिसमें डैम्पर नहीं है. ठीक है, इट इज अनडैम्प्ड फ्री ऑसिलेशन. द सेकंड पार्ट ऑफ द मोशन इज डैम्प्ड फ्री ऑसिलेशन. ठीक है, तो दो अलग अलग मोशंस को क्लब करा गया है. That is why I thought that this is a problem which is going to be good enough to be discussed in this class. Okay. Anyhow, anything else? Okay, then in that case, if everything is clear, so let me just conclude this session for today, and okay then, thank you. Have a nice day.